Today's experiment in calorimetry, we're going to do two different parts. One is where we're going to look at a simple heat transfer from a hot metal to water, and in the other one we're going to look at a chemical reaction. And in both we'll look at the temperature change in the water and determine something about either the metal or of the reaction. So some definitions here. Specific heat, the units for it are joules per gram degree C. It is a physical property and it has to do with how much energy something has to absorb in order to warm up, or it also could be how much energy is released when something cools. So either way, if something is warming or cooling, this gives you that relationship. You should note that metals usually have a low specific heat. They require very little energy to warm. And something like water is considered to have a high specific heat. It takes a lot of absorbing a lot of energy in order for it to warm up. Heat, of course, is Q, and Q has a sign. Q is positive for an object that is warming and negative for an object that is cooling. Thermal equilibrium is when two objects reach the same temperature. So if you have a hot object and a cold object, heat will flow. It always flows from hot to cold until they're both at the same temperature. And when they reach the same temperature, we call that thermal equilibrium. And this is important for ours because when we put our hot metal into our water, if given time, eventually the temperature of the metal and the temperature of the water will be the same. Okay, and this equation I have started writing this way just because it looks like Q smat that way, and you can kind of say it like Pivnert. But anyway, let's do some units. So Q is measured, it's heat, and it's measured in joules. S is the specific heat, and it's in joules per gram degree C. Mass, of course, in grams, and temperature, we use Celsius. Okay, first experiment we're going to look at is with the hot metal. So we're going to heat some metal by having it submerged in boiling water. And then we'll have a cup of water, or measure the temperature of it before. Then we'll pour our hot metal in, and of course the water will warm up. The hot metal will give heat to the water, and we'll measure the temperature change in the water. And from that, we'll be able to determine the specific heat of our unknown metal. So let's just go through and mark some. So this is the metal, mass of the metal. This is T1 for the metal. This is the mass of the water. This is T1 for the water. This is T2 for the water. Okay, let's see what we can do. So delta T, it's going to be T2 minus T1, both for the water, of course. And so T2 is 29.1 minus T1. Watch our sig figs on this. This is a positive number. Sometimes I like to, when you're doing chemistry or thermodynamics, it's good to kind of keep those positive signs just to kind of make sure that you're watching the signs, because positive and negative changes everything. To get the delta T for the metal, we need the T2 for the metal. And so what we were saying is that at thermal equilibrium, that is the same as the T2 for the water. They will both reach the same temperature in the end. So let me make a little line so that I'm not. Okay, so a weird way to write it, but watching my sig figs, remember when you're adding and subtracting, you look at how far they go to the right, and that's why I did my sig figs that way. Okay, the heat gained by the water. So for the water, the relationship between heat and temperature change. And I'm going to make sure I put in all the numbers for the water on these. So water specific heat. The mass of the water was 48 grams, and the delta T for the water So watch the sig figs really on this part, and I expect you to carry extra digits because a lot of times our temperature change drops down to 1, 2, sometimes it has 3 sig figs, but a lot of times it will limit your sig figs in your Q. And this amount of heat you're going to use in another step. So I'm just going to kind of mark, I'm going to keep that it has that many. For my answer here, the amount of heat gained, I am going to write it with the correct number of sig figs, which is 2. But when I go on, I'm going to use this bigger number. So how much heat was lost by the metal? So to get the Q for the metal, let me just use this. We know that the Q for the water is the same number and opposite sign as the Q for the metal. Let me write it like this. Okay, so I know for the Q for the metal, it's going to be negative. But that's not what it asked. It didn't ask for the Q for the metal, it asked how much was lost. And so it is true that I would say since I have that word lost, that takes the place of the negative sign. Negative does mean it's losing it, so that would be redundant to not have that. You can't. Another way to think about it is you can't lose a negative amount, something that would be gaining. So anyway, so now we're ready to do the specific heat of the metal. So we're going to do our Q SMAT, but then put in all the numbers for the metal. For the Q for the metal, I'm going to use this whole thing. Carry extra digits. That was the mass of the metal that was given. And that is a small specific heat, which is what you expect for a metal. It definitely should never be over that of water.